Okay, hello. Hi, everybody. Thank you for coming here today. So my name is Garrett Goon. I'm at IBM Research, and I'll be talking about our journey with TorchTitan and some of our collaborations with the PyTorch team at IBM Research. So first of all, thanks for the opportunity to speak. This was prepared with my colleague Linsong Chu, who unfortunately couldn't be here today, but I'll be talking about our work together. A brief timeline. So we were, I would say, interested very early, for sure, in TorchTitan, which I'll explain a bit more about what that is in a second. And I'll talk about the early exploration period, what made us interested. Later, I'll talk about how in April of last year, we started evaluating TorchTitan as a framework for doing real full-scale production runs for some work at IBM Research. I'll go into some more details about how those production runs went and all the really nice performance features of TorchTitan that we found in those runs. And I'll then stop with some reflections on what's changing recently and where TorchTitan is going, the things that we're excited about with TorchTitan. So what is TorchTitan? TorchTitan is a Torch native platform for large-scale training. That means mostly pre-training, mostly large language models right now. But it's really nice in that it's totally native. No external dependencies. It shows you how to do full end-to-end runs with fully sharded data parallel, tensor parallel, pipeline parallel, all the things you would want, and how to combine them in a Torch native way. And it's something we've been following since the days when it wasn't even called TorchTitan. It used to be called TorchTrain, but it's graduated from the PyTorch Labs days. And so in this early period, so at IBM Research, we have our own open-sourced training stack, FMS FSDP, which we've used again in production runs. And so first, why consider looking at other options here? This was the kind of evaluation phase. And at this time period, when TorchTitan was first coming out, they were equally performant. There was no performance reason to change. They're quite similar in that they were based on fully sharded data parallel, both of them. But there were some really promising developments that were catching our eye. So one was, at the time, upcoming support for FP8 training. I'll talk a lot more about that later on, and the nice benefits you get from FP8 in TorchTitan. This was the time when FSDP2 was also coming out, so this is the fully shard API, for those of you familiar with that. I would say a more ergonomic API, also more performant, something else we were interested in. But probably the main thing was PyTorch's excellent history of building these great, super useful repos, building great communities, and the promise of what was to come in the TorchTitan development. So we also work quite closely with PyTorch at IBM Research. This is one of the quite relevant collaborations that we had at this phase that made its way into TorchTitan. So here, this had to do with activation checkpointing, which is a method where you don't save all the activations in the forward pass, but you recompute them in the backwards for memory savings. And it was, at the time, very standard to checkpoint every block, every layer in your model. But in our runs, this was not quite flexible enough. We wanted to do more selective checkpointing. This originated in FMS FSDP, and through collaboration with PyTorch, this eventually made its way into TorchTitan. If you're interested, you could read more in this blog post. And this is part of an evolution of more and more advanced activation checkpointing in PyTorch. So now you don't just have to checkpoint at the block level, you can do it at the level of individual Torch ops. But anyway, part of a nice story that's continued to improve to this day. So in April of 2024, this is when, feels like forever ago now, but this is when LLaMA 3 was released. And internally at IBM Research, we started a project to replicate the full LLaMA 3 70B training model training run. Why is 70B? So it's been used, it continues to be used as a research vehicle at IBM Research. So a lot of our previous work tended to focus on smaller models, or maybe not so small back at the time, which are really good for quick iteration, data ablation, novel architecture, exploration, speculative decoding, things like that. But a 70B model is more in the Goldilocks zone, where it's much larger, but you don't need too specialized training to train it well. Things we're already familiar with, we're good enough. There's strong inference support, all the support that LLaMA models have. And it's just more capable, of course. So it's a strong test bed for more advanced workflows like RL, tool calling, agentic uses, that kind of thing. But it was still not maybe obvious at the time whether TorchTitan was fully ready. And so our collaboration with the PyTorch team continued. So this is one blog post you can read about improving checkpointing. So rather than writing to disk, writing to persistent storage in a blocking way, you can do much, much better if you offload it to a non-blocking thread. Here are some performance plots of the kinds of improvements you get with this strategy. These are features that are now fully integrated into TorchTitan. It's just a flag you set if you want to use this. And the other part, which I've already alluded to before, was the float 8 training. And so in this collaboration, we again worked with the PyTorch team to demonstrate the efficacy of using lower precision D types. So this again was fully benchmarked in TorchTitan, in November of last year. Here we're using float 8 in 2 different ways. So both for the linear layers, that is float 8 matrix multiplies, but also float 8 all gathers for fully sharded data parallel. So rather than doing the all gather in bfloat 16, you save half the bandwidth, and it makes quite an improvement. So 50% throughput speed up. Again, a feature that is today in TorchTitan and very easy and profitable to use. So the actual training run started in late 2024. And here we built off of the snapshot of Titan that was available in August. But to actually make it production ready, we needed to add a few things. A lot of them on this slide are now available in upstream TorchTitan, but at the time, things like weights and biases support didn't exist. You couldn't log to weights and biases, a small thing, but important for tracking the status of the run. We also needed a Hugging Face adapter. So in TorchTitan, the native way to save checkpoints is with the distributed checkpointing API, where you get many small files, which to use, you want to coalesce together into a single Hugging Face model. You want to run evaluation, you want to do anything that touches the Hugging Face universe. Having an adapter like that is super important. Other things we needed were more flexible checkpoint resuming. So after a model failure, you want to load back the weights and the optimizer state. But for other use cases, you might just want to load the weights again. That was something important to us. And another feature was having more fine-grained control on the global batch size. So in training, your resources may change, more GPUs may become available, or some might go away. And you want to be able to continue training while having the same global batch size or increase batch size as you go in training. So gradient accumulation didn't exist at the time, so that's something we also needed to implement. And later on, we also did longer context training for 70B, where we used advanced positional embeddings like Yarn, which some of you may be familiar with, for better long context performance. So one area where we especially found that we needed some additions, some improvements for production readiness was in the data loading. And here we were able to pull in some some aspects of our own training framework, FMS, FSDP, and had a bunch of features that we found necessary for really doing runs at scale. So the first one is rescalability. So again, the resources weren't always constant over training. And if you're going to train on a different number of GPUs, ideally, you'd have it such that the data comes out in exactly the same way as in your original resource setup. So our data loader implements this feature. It also is capable of other things like handling pre-tokenized data, or if you need to, it can tokenize on the fly. There is a very efficient memory efficient shuffle. So some of the kind of stock options in Torch have quite high memory constraints if you want to shuffle. There's also more advanced multi-data set sampling. So if you're combining data sets, you want to weight them in particular ratios. This is also implemented, and it's all fully checkpointed, of course. So if your training run dies, you can resume, and you'll be guaranteed, of course, to continue just where you left off in terms of the data. If you're interested in this, we had a talk on this last year, Davis and Linsong, our colleagues from IBM Research. Check out that YouTube video from last year's conference. Okay, so in late 2024 is when our actual full-scale pre-training run was kicked off. So again, 100% based on TorchTitan. It really uses mostly stock TorchTitan with a few of those quality of life improvements that we talked about. And the main takeaway is that we were able to get to the same 7 dB evaluations in a third of the GPU hours using TorchTitan. So where does this come from? Some of this comes from the FP8 improvements. So that's the 1.5x throughput enhancement from FP8 map moles and FP8 FSDP2 all gathers. And other advancements also let us hit those evaluation marks in half the token budget. And the main takeaway here is that, with some amount of small additions, really TorchTitan is ready for end-to-end training. It's a proof point, especially where it is today, that you can do full end-to-end production level training in TorchTitan. So with this model, we've continued to work on this in 2025. Some of this is, again, TorchTitan based, so really long context extensions using native TorchTitan context parallelism. So that's when you have a really long sequence and you split it in the sequence dimension. That kind of thing is supported in TorchTitan. And continuing post-training outside of Titan. So last, I want to talk a bit about trends in TorchTitan that we're seeing now. These are things that I think are really fun and exciting. TorchTitan is really showcasing some of the capabilities of stock PyTorch with some of the work that's going on here. And essentially the things that are changing is that there are new models that require really fundamentally different training paradigms or fundamentally different layers and building blocks to train them well. And yeah, it's all architecture driven. So TorchTitan originally was very LLaMA centric. There was just the one model, just LLaMA. And it was great, it showed you how to do everything with LLaMA. So tensor parallel, pipeline parallel, just like everything you want, how to combine them, how to do it in Torch. But at some point that is a little narrow. And now we have more options. So fairly recently, there's a full implementation of DeepSeek v3. There's also an implementation of Qwen 3. It's a little more experimental, but there's also diffusion models. Examples of that in TorchTitan. But it's really the kind of first two categories that have driven, I think, a lot of the recent fun changes in TorchTitan. And it's the need of mixture of experts that I know we've heard a lot about and we'll continue to keep hearing about at this conference. Mixture of experts has been a real forcing function for some of the changes and advancements in TorchTitan of late. Work continues in collaborating with the PyTorch team in these aspects. So mixture of experts, they require some more specialized kernels. In this blog post, we discuss one approach to these kernels and benchmark it in TorchTitan. If you're interested, please do check out that blog. But the main thing I think is really exciting is the rapidly maturing expert parallel support in TorchTitan. So for these mixture of experts models, they're defining features that they have these huge weights, where logically they correspond to like different experts. And the native way, the natural, most advantageous way of training these models is expert parallelism, where you put different experts statically on different GPUs. So, on GPU 0, you get some slice, MOE 0, some chunk of the experts. Another chunk goes on GPU 1, and so on and so forth. And then you just communicate. Some kind of communication is required across GPUs in order to correctly train the model. And this is actually not easy to get right. And there have been a lot of improvements in the TorchTitan ecosystem for supporting this. So it's quite easy to get the gradients wrong. To get them wrong by a factor, but that's done correctly in TorchTitan. You do get the correct gradients. There are specific settings for fully shard, the FSDP2 API that you'll want to use for expert parallel training. These are also handled correctly as of late in TorchTitan. It's also important to balance your loads well. So different numbers of tokens are routed to different experts in this strategy, and you don't want to become too imbalanced. So there's mechanisms for helping enforce that balance that work in TorchTitan. And there's the possibility of also having custom metrics that visualize that routing, that any imbalance you might have, which is also super helpful in practice. Some of you might have come from the symmetric memory talk from before. A future direction, which I know is being worked on for TorchTitan integration, is a GPU-initiated all-to-all. That has to do with the communications we need for expert parallel. Not available yet, but it's coming, and that'll be a huge help. So very, very excited for that in the future of TorchTitan. One byproduct of this work of late, where we're adding new architectures, new models, is that it's easier than ever to integrate your own models into TorchTitan. This was not, I would say, not always the easiest, but it's a much smoother path today. So as an example of this, we do a lot of experimentation on top of TorchTitan at IBM. One recent project was to build MOE hybrid models, where you have a mixture of experts like we've talked about, but instead of just having standard attention layers, you also have novel linear attention variants, this Mamba 2, for anyone familiar, interspersed. And TorchTitan has been a really nice framework for doing that kind of experimentation in a mature way. So you might have also heard earlier today in the keynote that IBM, we have our own accelerator, the Spyre card. And TorchTitan is in a mature enough state where it's also useful for Spyre development in the following way. So for this new chip, for this new card, we need constant testing of prioritized models. So of LLaMA models, of Granite models, and this gets expensive quickly. So if you're using, say, a full 8 billion parameter model for this testing, it just takes too long. And so what is more useful is to have essentially truncated versions of that model. So instead of having all 28 layers, however many, you just have a few. The tensor shapes are the same size, so it is a real proper test of the Spyre hardware. But you also can't just use random models. So if it's a random model, it's just too not representative of what the actual models will do. The numerics are different, the distributions are different. And so you need tiny models for this kind of training, for this kind of testing to really capture everything you'd want. And so we're using TorchTitan to build these tiny models. And it's really helped a lot. So there's quicker development time around. reduced CI/CD budgets. It's been a huge help. And today, TorchTitan has, I think, all the infrastructure you need to make this easy, to make it kind of plug and play for building these tiny models. And TorchTitan, its main use case is training at scale. But again, it's mature enough that even if you're just doing tiny model training, it's a good place to start. This is an example of one of these models, this 1 billion parameter 3-layer model on Hugging Face. There is a Spyre plugin into VLLM, and having references to these models in PRs or using them to test PRs has been a big productivity gain for us. So yeah, there's more I could say on TorchTitan, but I think I'll leave with just some final thoughts. One of the things that I've personally really loved about TorchTitan and the way I view it is that it's an excellent source for docs and tutorials about the latest Torch features. So either both for nightly features or just for really advanced features and how to use them properly. And not just in isolation with some tiny snippet that might not give you all the context you need. You see how they're used in a full end-to-end code base. So some examples of this, like one, what are the best practices for the fully shard API? There's a lot of flags here. It's not necessarily obvious how to use them. Like I talked a bit before, for expert parallel, there are very specific best practices to use. Sometimes you want to reshard after the forward pass, sometimes you don't. And TorchTitan is a good reference point for what the state-of-the-art usage is. Say you want to do really long context training and you don't want to pull in third-party dependencies. You can reference TorchTitan for how to do context parallel training, where you can scale up to very, very long sequence lengths. For going back to MOEs, there are, I think, still private ops for doing the specific kind of matmls that you want to do for mixture of experts, this grouped MM. And the kind of best documentation for this is in TorchTitan. It shows you what the arguments should look like, what the shapes are, where exactly you call that. And another example on this point is for expert parallel. So how do you use the detensor APIs for distributing your mixture of experts model over many GPUs? How do you hook it up so that the right all-to-all communication patterns are automatically applied in an elegant way? For the practitioners out there, I do have some points of advice that we found in our development. And basically, it is particularly important, I'd say, to pin to a snapshot of Titan. And some things aren't so special here. The code changes rapidly, but that's not so different from other repos. But another thing that can be a bit of a headache is that TorchTitan also does pull in regularly new nightly features. And that means you might also have to rebuild your total environment that you're training on. If you're using an image, then it might start failing if you pull in new TorchTitan code, things like that. There are many opportunities to contribute. It is in a mature state, but there's many quality of life places where there have been recent improvements, from making it easier to add new models or configure models in custom ways, to add more custom metrics to your usage of TorchTitan, and many underlying performance parts that can be improved as well. So please do consider contributing. And I'll end with just a thank you to the whole PyTorch team and the TorchTitan community. We've had a really nice experience with this, and just thank you all. So the question was, who are the target users of the software? I think it is useful for a variety of users. So I mean, one, as we've seen, you can use it for full end-to-end production runs, with some modifications. I think it is great for research too. So you can fairly quickly iterate on model design, training strategy, things like that, and you get a lot of the infrastructure you want for free. So you don't have to worry about checkpointing. You don't really have to worry about proper parallelization strategy. I think it does let you focus pretty well on the models, if that's your use case. So the question was about the largest cluster that we've run TorchTitan on and the performance, and I think I will avoid answering that question. Thank you. Yeah, sorry, I can't answer more on that point. So the question was about nickel environment variables. So I don't think on our end that we needed, let me not say something wrong. We do certainly have specific nickel configurations for our cluster, and there are some set in TorchTitan. I don't know how they differ off the top of my head, but that's a good question. Those things do matter. Yeah, so the question was for the async checkpointing, how does the memory usage compare? I think this is actually touched on either in the blog post or there's a PyTorch developer post on the same subject. I think there was at least an experimental option for zero copy where I think there is no extra memory overhead, if I believe. I mean, this is all CPU memory too. It's not like a copy in GPU. I don't know today what the default is, whether there is an extra CPU memory overhead copy required. I'd have to check. Sorry, if we've integrated with what? There is fault tolerance integration into TorchTitan. That's not something I've worked on much myself, but I know there are various Torch FT flags that are available. I'm not sure the degree of integration and what's available yet. Our training was pretty stable, so it wasn't such a concern for us. Yeah, so in terms of comparison between TorchTitan and other frameworks, I mean, I think, I guess I don't know this, but my sense was that TorchTitan was intended as a Megatron replacement. That's always somewhat how I think of it. I think it is a lot more ergonomic to use, so I've personally used Deep Speed, Megatron, these kinds of things, and really having the very Torch native design here is super, super helpful, I think. I think it's very clean and understandable in ways that I did not always find to be the case in some other frameworks. So it's been a very positive experience for my use cases. I'm sorry, I couldn't quite hear that. Oh, it is mostly native. Are you asking like whether there are custom Triton kernels or things like that? So it's mostly Torch native ops. In some of the MOE parts, there are a few Triton kernels that I think are still used there, but for 99% of the cases, it's very much stock PyTorch. Oh, sorry, I got to wrap up. Yeah. All right, thank you all.